Hello and welcome to this video for OCR A-Level Physics in the module of forces of motion in the topic Newton's laws of momentum and on the concept of Newton's first and second laws. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe Newton's first law of motion, define and describe Newton's second law of motion, and calculate values based on Newton's second law of motion. So in this lesson we're going to look at the following parts of the OCR A-Level Physics specification, in particular Newton's three laws of motion. Now Isaac Newton looked at how we can explain how an object moves in terms of forces which change its motion. So one key idea of physics is Newton's laws of motion. Now these were the laws which everyday objects obey, and they determine the motion of these objects. Now they were published by Sir Isaac Newton in 1687 in his book De Principia Mathematica, The Principles of Mathematics. Now this book is actually a trilogy, and actually book 1 concerns Newton's laws of motion. Now these laws explain all motion in the everyday universe. There are no exceptions to Newton's laws. Now they are the most important laws of the everyday universe. So Isaac Newton looked at how he could explain the object moves in terms of forces, which we now call dynamics. So this resulted in Newton's laws of motion, which can describe the relationships between forces acting on an object and its motion. Now, the importance of Newton's laws of motion lies in their ability to explain a wide range of different phenomena, from the motion of planets to the behaviour of subatomic particles. Now, by understanding these laws, we can predict and explain the behaviour of objects in motion, allowing us to design and engineer systems that work effectively and safely. Now together, Newton's laws of motion provide a framework for understanding the fundamental principles of motion and force, which underlie many areas of science and engineering. They form the basis for classical mechanics, the study of motion of objects under the influence of forces, and are therefore a cornerstone of modern physics. Now their significance can be seen in many everyday applications, from the design of bridges and buildings to the development of space exploration technologies. Now in the 17th century, astronomers began to use telescopes to observe the night sky, and they saw objects such as planets could move freely through space. They simply kept on moving without anything providing a force to push them. Now Galileo came to the conclusion that this was the natural motion of objects. So it was considered that an object at rest will stay at rest unless a force causes it to start moving. A moving object will continue to move at a steady speed in a straight line unless a force acts on it. So objects move with a constant velocity unless a resultant force acts on them. Now being stationary is actually just a particular case of this, where our velocity is equal to 0. Now the tendency of a moving object to carry on moving is known as inertia. So an object with a large mass is difficult to stop moving. Think about catching a cricket ball compared to a tennis ball. Similarly, a stationary object with a large mass is difficult to start moving. So think about pushing a car to get it started. Now it's difficult to make a massive object change direction. So think about the way a fully laden supermarket trolley tries to keep moving in a straight line. Now all these examples suggest another way to think about an object's mass. It's a measure of its inertia, how difficult it is to change the object's motion. So uniform motion is the natural state of motion of an object. So when we say uniform motion, we mean moving with a constant velocity or moving at a steady speed in a straight line. Now, inertia is an everyday experience we encounter in all our lives. For example, a passenger in a car feels like they're being pushed backwards when the car accelerates forwards. This is because the passenger's body has inertia and resists the change in the motion of the car. When you try to push a heavy box, it may be difficult to get it moving because there's a large amount of inertia. When a football is kicked, it moves forward in a straight line until it's acted upon by an external force, such as friction from the ground. When a roller coaster goes over a hill, the riders tend to lift out their seats because their bodies want to keep moving in a straight line whilst the roller coaster changes direction. So when you turn a corner in a car, you may feel like you're being pushed to the side. That's because your body wants to keep moving in a straight line whilst the car changes direction. Now we are aware that if an object has a high mass, it has a high inertia. If it has a low mass, it has a low inertia. Now this leads to Newton's first law of motion. An object will remain at rest or in a state of uniform motion unless acted upon by a resultant force. This means that a body will stand still or move in a straight line at a constant speed unless there is a resultant force acting on it. So if the forces acting on a body are not balanced, the overall resultant force will make the body accelerate. So this could be a change in the object's speed, the direction, or both. Now, a resultant force is an overall force on an object. The resultant force is our observed force acting on an object. So the resultant force can replace the other forces in a diagram. So the number of forces acting on an object can be replaced by a single force that has the same effect as all the original forces acting together. Now, we should be aware that objects accelerate in the same direction as the resultant force that acts upon it. So if a resultant force acts on a stationary object, it will cause the object to accelerate in that direction. If the resultant force acts in the same direction of motion as a moving object, it will cause the object to accelerate in that direction by increasing its speed. If the resultant force acts in the opposite direction of motion for a moving object, it will cause the object to accelerate in that direction by decreasing its speed. And if a resultant force acts in a perpendicular direction of motion as a moving object, it will cause the object to accelerate by changing its direction of motion, but not its speed. Now, Newton's second law of motion says that the acceleration of an object is proportional to the resultant force acting upon it. This can be written as the equation F equals ma, where F is the resultant force, m is the inertial mass, and a is the acceleration. This indicates that the greater the resultant force acting on an inertial mass, the more acceleration that you will get. It indicates that for a given resultant force, the more inertial mass you have, the less acceleration you get, which indicates that mass is an inertial mass as it provides a tendency for inertia. So the mass of an object, as we said, is a measure of its inertia, or its ability to resist any change to its motion. So, the greater the mass, the smaller the acceleration which results. So if you push your hardest against a small car, which has a small mass, you will have a greater effect than if you push against a more massive car. Remember, the resultant force acting on an object is the vector sum of all the forces acting on the object. The acceleration is always produced in the same direction as the resultant force, and this law of motion can only apply to objects with a constant mass. So this equation can be applied to any situation where there is a resultant force acting on an object of constant mass. So for a given object, the acceleration is directly proportional to the force. Now, if the net force acting on an object is non-zero, but in the opposite direction to the motion, the object will decelerate. So for a constant force, the acceleration is inversely proportional to the mass. Now, in this case, if the net force acting on an object is zero, according to Newton's second law, the acceleration of the object will also be zero. So in this case, the object will either be at rest or continue moving at a constant velocity, following Newton's first law of motion. So if we've learnt in today's lesson, we should have knowledge and applications of the laws of motions in appropriate situations, and we use F equals ma for situations where the mass is constant. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe Newton's first law of motion, define and describe Newton's second law of motion, and understand how to calculate values based on Newton's second law of motion. Hello and welcome to this video for OCR A-Level Physics on the Forces in Motion module in the topic of Newton's law and momentum, looking at the concept of Newton's third law. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe Newton's third law of motion, detail Newton's third law pairs, and calculate values based on Newton's laws of motion. So in this lesson, we're going to be looking at the following parts of the OCR A-Level Physics specification. 3.5.1 Newton's laws of motion. Now, when two objects interact, each exerts a force on the other. Now, Newton's third law says that these forces are equal and opposite to each other. So this leads to the following Newton's law of motion. When two bodies interact, the forces they exert on each other are equal in magnitude and opposite in direction. Now, these two forces are sometimes described as an action and reaction, but this is quite misleading, as it sounds as though one force arises as a consequence of the other. In fact, the two forces appear at the same time, and we can't say that one caused the other. Now, you can hear this law as every action has an equal but opposite reaction. Now, this isn't a good way to describe this law, as it implies that the forces are both applied to the same object. Now if this was the case, then you will get a resultant force of 0 and inertia for all objects. Now the two forces which make up a Newton's third law pair must have the following characteristics. They must act on different objects. They must be equal in magnitude. They must be opposite in direction, and they must be forces of the same type. So for example, two objects may attract each other because of the gravity of their masses, so it would be two gravitational forces. For example, two objects may attract or repel each other because of their electrical charges, the electrical force. Two objects may touch each other, so contact forces. Two objects may be attached by a string and pull on each other, so tension forces. Or two objects may attract and repel because of their magnetic fields, being magnetic forces. Now the two forces in Newton's third law of motion represent the same interaction seen from two different perspectives. So for example, if you push against a wall, the wall will push back against you just as hard. When you stop pushing, so does the wall. If you pull a cart, whatever force you exert on the rope exerts the exact opposite pull on you. When you go swimming, you push back against the water with your arms and legs, and the water pushes you forward with an equal sized force. Now Newton's third law applies in all situations and to all types of force, but remember, the pairs of forces are always the same type of force, have the same magnitude, and act on different objects. So sometimes it looks like Newton's third law is being applied, but actually it's not. So you must be very careful when trying to work out if forces are Newton's third law pairs. So consider a person standing on the surface of the Earth. Now the two gravitational forces observed in this diagram are a Newton's third law pair, as are the two contact forces. But do not be misled into thinking that a person's weight and the contact force of the floor or the earth are a Newton's third law pair. Although they are equal and opposite, they do not act on the same object. They act on different objects, and they are not of the same type. So, as we said before, Newton's third law applies in all situations and to all types of forces. The forces must be of the same type. Now, like we said, sometimes it looks like Newton's third law is being applied, but actually it's not. So if we consider the gravitational force acting on the man and the contact force from the earth on the man, they are equal but opposite, so the resultant force is 0, so the man does not accelerate. However, because both forces act on the same object, it is an example of Newton's first law of motion, not Newton's third law of motion. So Newton's laws of motion can be summarized as the following. Newton's first law: the velocity of an object is unchanged unless a resultant force acts on it. Newton's second law: the acceleration of an object is proportional to the resultant force acting upon it, F equals ma. And Newton's third law: when two bodies interact, the forces they exert on each other are equal in magnitude and opposite in direction. Now there are many applications of Newton's laws of motion in the real world. Examples include in engineering, such as structural designs, where engineers use Newton's laws to design buildings, bridges and other structures. They analyse the forces acting on different components to ensure structural integrity. Transportation: understanding Newton's laws can help engineers design vehicles like cars, planes and spacecraft by considering factors like acceleration, braking and stability. And in mechanical systems, machines and engines rely on the principles of Newton's laws to function effectively and efficiently. In physics, in astronomy, Newton's laws explain the motion of celestial bodies, including planets and moons and comets. They form the basis of gravitational theory and help us predict and understand astronomical phenomena. And in particle physics, Newton's laws are fundamental in understanding the behaviours of subatomic particles in particle accelerators, allowing scientists to study the fundamental forces and particles of nature. In space exploration, rocket propulsion needs Newton's third law, as it allows the rockets to work because the ejection of high-speed gases generate a reactive force that propels a rocket forward. And in orbital mechanics, Newton's laws play a crucial role in calculating trajectories, orbital manoeuvres and planning missions in space exploration. So we can apply Newton's laws of motion to any situation in the universe, for example riding the bus. So for Newton's first law, you'll get on the bus and stand up. When the bus is stationary, you feel no force. When the bus accelerates, you feel a backwards force. You want to stay where you are, but the bus forces you to move. When the bus is at a constant speed, you feel no forwards or backwards forces. The bus slows down and you feel a forward force. You want to keep moving at the same speed, but the bus is slowing down, so you fall forwards. If the bus turns left, you want to keep moving in a straight line, so you're forced to the right. If the bus turns right, you want to keep moving in a straight line, so you're forced to the left. Newton's second law. As more people get on the bus, its mass increases. If the driving force of the bus's engine is constant, we can see it takes longer for the bus to gain speed. And finally, Newton's third law. As you stand on the bus, you are pushing down on the floor with a force that is equal to your weight. But if that was the only force acting, you will begin to move through the floor. So therefore, there is an equal but opposite force from the earth on you. There is also a normal force from the floor onto the human and from the human onto the floor. We can also look at the situation of taking the lift. With Newton's first law, when you get into the lift and when it moves at a constant speed, you feel no force up or down. When it sets off going up, you feel like you're being pushed down as you want to stay where you are. When it sets off going down, you feel like you are lighter, you feel getting pulled up. In terms of the second law, as more people get into the lift, its mass increases. If the lifting force is constant, we can see it takes longer for the lift to get moving. Or we can see that with more people, the greater the lifting force must be. And finally, with Newton's third law, as you stand in the lift, there's a weight downwards to the earth, but there's also an equal but opposite force from the earth to you. In addition, there's a normal force upwards from the floor to your feet, and there's a normal force downwards from the feet to the floor. So that brings an end to our lesson today. If we've learned in today's lesson, we should have a knowledge and application of the three laws of motion in appropriate situations, and know F equals ma for situations where the mass is constant. So if we've been successful and we've learned in today's lesson, we can define and describe Newton's third law of motion, detail Newton's third law pairs, and calculate values based on the laws of motion. Hello and welcome to this lesson, which is part of the Forces of Motion module for OCR A-Level Physics in the topic of Newton's laws and momentum, looking at the concept of momentum and impulse. So if we've been successful and we've learned in today's lesson, we should be able to define and describe momentum and impulse, calculate momentum and impulse, and link momentum and impulse to Newton's laws of motion. So in this lesson, we're going to look at the following part of the OCR A-Level Physics specification. In particular, looking at linear momentum, that net force is the rate of change of momentum, the impulse of a force, and how it links to force-time graphs. So, linear momentum is how difficult it is for an object to change its motion when it is moving in a straight line. If it is difficult for an object to change its motion, it has a high momentum. If it is easy for an object to change its motion, it has a low momentum. Now the concepts of momentum and inertia are very closely linked to each other. Inertia describes an object's resistance to change in motion or lack of motion, and momentum describes how much motion it has. So momentum is your force or speed of movement, but inertia is what keeps you going. So momentum represents the amount of motion an object has, so we can think of it as a measure of the kinetic energy of an object. Now, inertia is a characteristic of an object that resists changes to its state of motion. Now, objects which are harder to move, or whose motion is harder to change, will have more inertia. So, momentum is a vector quantity because there's a product of a vector quantity, velocity, and a scalar quantity, mass. So momentum has both magnitude and direction, and its direction is the same as the direction of an object's velocity. So, linear momentum of an object is dependent on two factors of the object, the mass of the object and the velocity of the object. Now, we can express this in the form of an equation, that momentum is equal to mass times by velocity. Now this is why momentum is similar to kinetic energy. It contains the same terms. So whilst momentum is mass times by velocity, kinetic energy is a half times by mass times by velocity squared. Now we can symbolize the equation for momentum as P equals mv. Now linear momentum is given the symbol P as it is the first letter of the Latin translation of momentum or impetus. Now, Isaac Newton realised that a resultant force was needed to change the velocity of an object. Now, Newton realised that the effect of the resultant force depended on the object's mass. Now, it's better here to term mass as inertial mass. So what he decided to do was simplify this system and consider the products of inertial mass and velocity, which he called the linear momentum. Now, what this means is that for objects with the same linear momentum, the larger the mass, the lower the velocity, and it means the smaller the mass, the higher the velocity. Now, the units of linear momentum are kilogram meters per second. Now, if an object is not moving, then it has no momentum. So we say momentum is a dynamic quantity. So every object which is in motion will have a non-zero momentum. Now, an object which is stationary will have no momentum, because if velocity was zero, well, then momentum would equal zero. So linear momentum is a vector quantity. The direction of a momentum is shown by the sign of the calculated value, either a positive or a negative. Now, objects moving in opposite directions have opposite signs. So this means that momentum can be changed by either altering the speed or the direction of the object. Now, unless stated in the question, you can assign which direction is the positive or negative in a question. So as we know, momentum is equal to mass times by velocity. Momentum has both a magnitude and a direction. It is a vector quantity. If objects are moving in opposite directions, they have opposite momentums, and this is signified by one value being positive and the other being a negative. So this indicates to us that the momentum is directly proportional to the mass of the object as long as the velocity of the object is constant. And it also indicates to us that momentum is directly proportional to the velocity of the object if the mass of the object is constant. Now, this allows us to write the laws of motion in terms of momentum. So Newton's first law, which is that objects either stay at rest or move with constant velocity unless acted upon by a resultant force, could also be said as a resultant force changes the linear momentum of an object. Whilst Newton's second law says that the resultant force equals the inertial mass times by the acceleration, we can write this as a resultant force is proportional to the change in linear momentum every second. And finally, we say Newton's third law is when two objects interact, they exert equal yet opposite forces of the same type on each other. Or we could say that for a system of objects, the total linear momentum of the system before equals the total linear momentum of the system afterwards, as long as there are no external forces on the system. Now, we can calculate the linear momentum of any object when considering its motion. So, for example, George Russell is driving in the French Grand Prix. The total mass of Russell in the car is 710 kilograms. He is travelling at a velocity of 120 meters per second. What is his momentum? Well, momentum is mass times by velocity, so it is 710 times by 120, so it's 85,200 kilogram meters per second. Now we can consider Newton's second law of motion for a constant mass. We know that F equals ma, and we also know that a is equal to the change in velocity over the change in time. So we can substitute that into that equation and say that F is equal to m delta v over delta t. Now we know that a change in momentum, delta p, is also equal to delta mv. So therefore, if we say that F equals delta mv over delta t, it says to us that the resultant force is equal to the rate of change of momentum. Now in this example, the resultant force must be in the same direction as the change in momentum. So this equation can predict the motion of an object subjected to forces, even when the mass changes with time, for example with a rocket. So this makes it an equation which can be used in more situations, not just a special case. So this statement effectively defines what we mean by resultant force. It's an interaction that causes an object's momentum to change. So we know that if an object's momentum is changing, there must be a resultant force acting upon it. Now we can find the size and the direction of the resultant force by measuring the rate of change of the object's momentum. Now remember, the change of momentum is the final momentum minus the initial momentum, or mv minus mu. So we could write the equation to be F equals mv minus mu over t, or F equals mv minus u over t, which therefore simplifies out again to F equals ma. So this shows us that the equation F equals ma is a special case of F equals delta mv over delta t for when acceleration is constant. We can finally write this out to say that F delta t is equal to delta mv. Now this is important because we can then define F delta t and delta mv as the impulse. So the impulse is a force that is applied for a certain time. The impulse causes a change in the linear momentum of an object. Now impulse is measured like momentum in kilogram meters per second, or more commonly Newton seconds. It refers to one object in a collision, and we know that the larger the impulse on an object, the greater its change in linear momentum. So we can define the impulse to be the product of the average force and the time taken for which the force acts on the object. So for example, we can calculate the impulse of any object when considering its motion. So calculate the impulse acting on a 900 kilogram car when its velocity changes from 5 meters per second to 30 meters per second. Now we know momentum is mass times by velocity. The initial momentum is 900 times by 5, which is 4,500 kilogram meters per second. The final momentum is 900 times by 30, or 27,000 kilogram meters per second. So the impulse is the change between the two values, which is 22,500 kilogram meters per second. We can also calculate the force acting on any object when considering its motion. So a train of mass 7,500 kilograms is moving with a momentum of 150,000 kilogram meters per second. The train driver applies the brakes for 15 seconds and the train's momentum decreases to 37,500 kilogram meters per second. Calculate the force applied by the brakes. So we know F is equal to delta mv over delta t. So delta mv is mv minus mu over delta t, so it's 37,500 minus 150,000 divided by the time, which is 15 seconds. So it's minus 7,500 newtons. The negative is important because it indicates to us that the force is acting in the opposite direction to motion. Now this concept can be used for any collision between objects such as them rebounding off walls. So if you've got an object which is rebounding off a wall, we can say that the initial momentum is equal to mu and the final momentum is minus mv. Now in this instance, the velocity is a negative as it's now acting in the opposite direction and momentum is a vector. So we know that force is equal to the change in momentum over the contact time. So the change in momentum is minus mv minus mu over t. Now if we know that the collision was elastic, well we can say that mv will equal mu in terms of magnitude because no energy is dissipated out of the system. So therefore we can say that the change is minus 2 mu over delta t. Now if the impact is oblique, then the horizontal components must be considered for this. So therefore we know that v would now become v cos theta and u would equal u cos theta. So if we had it now at an angle, it would be minus m cos theta v minus m cos theta u over t. And that allows us to work out the force acting on an object where the momentum is changed by rebounding. Now this also indicates to us that the lower the rate of change of momentum for a collision, the lower the resultant force produced on the objects colliding. So when the impact time is large, the resultant force produced on an object colliding is small. So if a speeding car crashes, then the time of the collision is very small, so the force can be huge, so this can be very dangerous. It's important to remember that the rate of change of momentum for an object is directly proportional to the impact force exerted on it, which, as we said before, is another way to express Newton's second law of motion, F equals ma. Now in fact, vehicles are designed to minimize the force exerted during a collision. That is why cars have crumple zones at the front and back. They're weak enough to crumple, but strong enough to do so slowly. This increases the time to change momentum, the rate of change is lowered, so it decreases the resultant force on the car. Car passengers have similar protection. Airbags and seatbelts help increase the time it takes for the passengers to stop. As the time to change momentum increases, the resultant force on that object, the person, decreases. So seatbelts will stretch slightly, increasing the time taken for the wearer to stop, lowering the rate of change of momentum. Airbags inflate before you hit the dashboard of a car, so the compressing air inside it slows you down more gradually than if you just hit the hard dashboard, lowering the rate of change of momentum. Bike helmets contain a crushable layer of foam which helps lengthen the time taken for you to stop in a crash, lowering the rate of change of momentum. This reduces the impact on your brain. Now, crash mats and cushioned playground flooring increases the time taken for you to stop if you fall on them, lowering the rate of change of momentum because they're made from soft, compressionable materials. So, the crash pads and the cushioned playground flooring will increase the time taken for you to stop if you fall on them, lowering the rate of change of momentum. So imagine trying to catch an egg. If we held our hand out and didn't move it, the egg would smash because the change in momentum, the impulse, happens in a short time, increasing the rate of change of momentum, making that impact force large. If we cup the egg and move our hands down as we catch it, we make it longer to come to a complete stop. This increases the contact time, lowering the rate of change of momentum, decreasing the impact force, and the eggs remain intact. If we imagine catching a cricket ball, if we didn't move our hands, it would hurt when the ball stopped in our hands because the change of momentum, the impulse, happens in a very short time, increasing the rate of change of momentum. This means the impact force is large, so you can break your fingers. So if we make the contact time longer, we reduce the impact force in our hands from the ball as it decreases the rate of change of momentum. And this is why cricketers move their hands down when they catch the ball. Now, packaging, especially for fragile items, uses bubble wrap or polyester packaging to reduce the impact forces that items experience in transit. This helps cushion the items by increasing the time over which they experience a force, lowering the change of momentum rate, which reduces the risk of damage. And in football, increasing the contact time is sometimes used to an advantage, as the longer the contact time, the larger the change in momentum. So when kicking a football, after a strong kick, the motions follow through. The momentum from the foot is then transferred to the ball. This creates a larger impulse, and then the ball has a higher velocity. So as we know, force is equal to the change in momentum over time, or the impulse over time. This is the force that's produced in the collision which changes the momentum of the object, which we call the impact force. So as we said before, whilst the total momentum of the system of the object stays constant, the momentum of one object can change. Now, in many collisions, the change in momentum is the same regardless of the time of the collision. The aim of all collisions involving humans is to have a low impact force. It decreases the chance of injury, and this is done by increasing the contact time as it decreases the rate of change of momentum. Increasing the contact time decreases the impact force experienced by the object. So as we mentioned before, crumple zones, padding, helmets, sidebars, crash mats, seat belts all increase the impact time for a collision, so the impact force experienced by an object is reduced. Remember, it's important to note that the change of momentum stays the same, so when the time taken increases, the rate of change of momentum decreases. So when the time taken increases, the change of momentum every second decreases. Now we can also show this information in a force time graph. In real life, forces are often not constant and will vary over time. So if the force is plotted against time, the impulse is equal to the area under the force time graph. Now, since the area under a curve is the y-axis times by the x-axis, it's force times by time, which as we know is the change in momentum or the impulse experienced by the object. So as we can see in a force time graph, the area under the line is going to be the change of momentum or the impulse. Now this is extremely useful when the force exerted is not a constant value for the collision. In this situation, to find the change in momentum or impulse, you must either count the squares or break up the area into different shapes. So you can see here the force time graph for a constant force and also for a changing force. Well, please do remember that as the impulse is the product of the average force exerted and the time, the area under a force time graph is always equal to the change in momentum even if the force is changing. So that brings us to the end of today's lesson, where we've looked at linear momentum, the vector nature of momentum, how net force is the rate of change of momentum, the impulse of a force, and the idea impulse is equal to the area under a force time graph. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe momentum and impulse, calculate momentum and impulse, and link momentum and impulse to Newton's laws of motion. Hello and welcome to this video on the conservation of momentum, which is part of the forces of motion module for OCR A-Level Physics in the subtopic of Newton's laws of momentum. So if we've been successful and we've learned in today's lesson, we should be able to define and describe the conservation of momentum, calculate values based on the conservation of momentum in one dimension, and calculate the values based on the conservation of momentum in two dimensions. So in this lesson, we're going to look at the following parts of the OCR A-Level Physics specification: 3.5.2 collisions. Now, the linear momentum of an object is dependent on two factors of the object: the mass of the object and the velocity of the object. Now, we can express this in the form of an equation that momentum is equal to mass times by velocity. Now, we know that momentum is similar to kinetic energy as it contains the same terms. Momentum is mass times by velocity, and kinetic energy is a half mv squared. Now, we can symbolize this equation with the symbols P equals mv. Now, linear momentum is given the symbol P as is the first letter of the Latin translation of momentum. Now, in collisions and explosions, the total momentum is conserved if the system is closed. So this means that the total momentum of a system before is the same as the total momentum of a system afterwards. So we can say the total momentum before the collision equals the total momentum afterwards. Now, this is derived from Newton's laws of motion. So we can say that the total momentum before, which is momentum 1 plus momentum 2, will equal the total momentum after, momentum 1 plus momentum 2. Now, the individual objects in the system can change their momentum in an event, but the overall momentum of the system must stay constant. So, for example, if beforehand object 1 had a momentum of 2 kg meters per second and object 2 had a momentum of 0 kg meters per second, well then afterwards object 1 could have a momentum of 1 kg meter per second, as can object 2. So whilst the individual objects have changed momentum, the total overall momentum has stayed the same. Now, for an individual object to change momentum and have an impulse acting on it, a resultant force must be placed on the object. Now, we can say that the total momentum before, which is mass 1 times by velocity 1 plus mass 2 times by velocity 2, must equal the total momentum afterwards, where mass 1 times by velocity 1 plus mass 2 times by velocity 2. Now, the definition of the law of conservation of momentum states that it only applies when no external forces act. Now, an external force is a force that acts on an object in a system or the system itself from outside the system. So common examples of external forces include friction or weight. Now, systems with no external forces may be described as closed or isolated. So, as we said, for a system of objects, the total momentum of the system before equals the total momentum of the system afterwards, as long as there's no external forces on the system. Now, this can be observed in a collision where objects hit each other and move away with each other. Or we can consider any system which has at least one dynamic object before contact a collision. Now, it's important to note that the momentums of individual objects in the systems can change, but the total momentum of the system must remain constant. Now, as the total momentum remains constant, when the mass of a moving object increases after a collision, the velocity will decrease. So it also indicates to us that if the mass of the object increases as the two objects couple together, their velocity will decrease. Or if an object splits, when the mass decreases, the velocity will increase. So let's consider the following collision. What's the velocity of the two balls stuck together after the collision? So the first step is to work out the momentum for the side of the collision you can do. So beforehand, it's 2 times by 5 plus 4 times by 0. So 10 plus 0 is 10 kg meters per second. You then remember that the total momentum before equals the total momentum afterwards. So the total momentum is 10 kg meters per second. Then finally, we can say that momentum is equal to mass times by velocity. So velocity is equal to momentum over mass. So it's 10 over 6, which is 1.7 meters per second. Now, in an explosion, the total momentum of a system is 0. So in an explosion, where the motion where an object starts at rest and moves away from each other conserves momentum. Beforehand, the object is not moving. This means it has a total momentum of 0. So for a momentum to be conserved, the total momentum of the system must be 0. Now, after an explosion, both objects have a non-zero momentum. Now, the two objects are produced as fragments of the initial object. Now, as we said, the total overall momentum must be zero because this conserves momentum. Now, this occurs as the individual momentums are in opposite signs. This means that one momentum is positive and the other momentum is negative. This occurs as the two fragments are moving in an opposite direction, and this opposite direction gives them opposite signs. So as we said, the overall total momentum of a system after the explosion must be zero to conserve momentum. So one will be positive, for example, plus 20 kilogram meters per second, and one will be negative, such as minus 20 kilogram meters per second, to get your overall answer to be 0 kilogram meters per second. Now, this is shown when you consider a gun and a bullet. The recoil in any explosion can be explained by the conservation of momentum. So the total momentum is equal to 0 because the total momentum before equals 0. So before it explodes, the gun and the bullet are not moving. So therefore, the system has no momentum. So this means the system has no total momentum, which must be conserved in any event such as an explosion. So when the object is fired, the gun has a momentum and so does the bullet. But they must cancel out to give a total value of 0 because the total momentum afterwards is 0. So this means that the gun goes in the opposite direction to the bullet. The gun has a recoil. Now, the gun has a much larger mass than the bullet. So since momentum is mass times by velocity, the gun must have a lower velocity than the bullet to have the same magnitude of momentum, because we need the same magnitude of momentum from either side. So we can say that the momentum of the bullet equals the momentum of the gun. So we can say the mass of the bullet times by the velocity of the bullet is equal to the mass of the gun times by the velocity of the gun, which we can rearrange to say that 0 is equal to the mass of the gun times by the velocity of the gun minus the mass of the bullet times by the velocity of the bullet. Or 0 is equal to mgvg minus mbvb. So let's have a look at the following example. What's the velocity of bomb fragment 1? So the first step is to work out the momentum for the fragment of the explosion you can do. So the momentum of fragment 2 is 2 times by 7, which is 14 kilogram meters per second. As the momentum before equals the momentum afterwards, if beforehand was 0, afterwards must equal 0. So this tells us if fragment 2 has a momentum of plus 14 kilogram meters per second, well then the momentum of fragment 1 must be minus 14 kilogram meters per second. We can then say that momentum is mass times by velocity, so velocity is momentum over mass, so it's minus 14 over 3 minus 4.7 meters per second. The negative value indicates that it's moving in the opposite direction to the other fragment. Now, momentum can be conserved in both one-dimensional and two-dimensional problems. A one-dimensional problem occurs when collisions take place in one plane, either the vertical or the horizontal. A two-dimensional problem occurs when collisions take place in both planes, both the horizontal and the vertical. Now, since momentum is a vector, in 2D it can be split up into its x and y components. So in collisions and interactions, the linear momentum is conserved in all directions. So using the conservation of linear momentum as well as resolving vectors, it's possible to calculate changes in momentum. So below shows an object A moving to the right with momentum. It collides with stationary object B. After the collision, A and B move off in different directions with momenta P1 and P2 respectively as shown. Since linear momentum must be conserved, the vector sum of P1 and P2, the total final momentum, must equal P, the initial momentum. So what you can therefore do is you can draw a vector triangle to add the two vectors together, P1 and P2, and then work out your value from this. Another example would be below shows a general collision involving two masses, M1 and M2. The white object travels at a velocity v0 and collides with the stationary black object. After the collision, the white object travels at theta 1 and it's with the original direction with velocity 1, and the black object travels at theta 2 with the velocity v2. Now, the momentum in any direction must be conserved. In this case, the momentum must remain the same in the x and the y direction. So we can say, horizontally, the total initial momentum is equal to the total final momentum. So it'll be m1v0 is equal to m1v1 cos theta 1 plus m2v2 cos theta 2, because we're now looking at the horizontal component of the velocity. And vertically, we know that the total initial momentum is equal to the total final momentum. So m1v0 equals m1v1 sine theta 1 plus m2v2 sine theta 2. Again, we're now looking at the vertical component of the velocity. So let's have a look at the following collision. A 160 gram white ball travelling at 4 meters per second hits a stationary 170 gram black ball. After the impact, the ball moves apart at approximately 90 degrees to each other. With the white ball travelling at 2.5 meters per second, calculate the final velocity of the black ball. So step 1 is to find the initial momentum of the white ball. So it's 160 times 10 to the minus 3 times by 4, which is 0.64 kilogram meters per second. The initial momentum of the black ball is 0 because it's stationary. Now the final momentum of the white ball after the impact is 160 times 10 to the minus 3 times by its new velocity, which is 2.5, which is 0.40 kilogram meters per second. We can then use this information to draw a vector diagram which sums those two values, the 0.40 kilogram meters per second and 0.64 kilogram meters per second. We can then use this triangle to have the Pythagorean theorem work out the final momentum, where we can say, as it's a right angle triangle, that p squared is going to equal 0.64 squared minus 0.40 squared. Now remember, 0.64 is going to be in the hypotenuse because it is the overall value afterwards. So therefore, it allows us to work out the initial component to start off with. Or to finish with, sorry. So therefore it's 0.64 squared minus 0.40 squared, which is 0.25. That square rooted is 0.50 kilogram meters per second. Now that's the momentum of the black ball. So therefore, what's the velocity? Well, we know that momentum is mass times by velocity. Velocity is momentum over velocity. So therefore it's going to be equal to 0.50 over 0.170, which is 2.9 meters per second. So in this lesson, we've looked at the principle of conservation of momentum. We've looked at collisions and interactions of bodies in 1 and 2 dimensions. So if we've been successful, and we've learnt in today's lesson, we can define and describe the conservation of momentum, calculate values based on the conservation of momentum in 1D, and calculate values based on the conservation of momentum in 2D. Hello and welcome to this video on elastic and inelastic collisions, which is part of the Forces and Motion module in OCR A-Level Physics in the subtopic of Newton's law and momentum. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe the conservation of momentum, define elastic and inelastic collisions, and calculate values in inelastic and elastic collisions. So we're going to be looking at the following part of the OCR A-Level Physics specification: collisions, in particular perfectly elastic and inelastic collisions. Now when objects in a system interact or collide, they can transfer two quantities, momentum and kinetic energy. Now momentum is always conserved in all collisions. This is because there is nothing else into which momentum can be converted to. But kinetic energy is not usually conserved in a collision because it can be transformed into other forms of energy. Now work can be done to form an object in collisions or be transferred to the internal energy of the surroundings in things such as heat or sound. Now of course the total amount of energy remains constant as prescribed by the principle of the conservation of energy. So this leads to two types of collisions: elastic collisions and inelastic collisions. Now elastic collisions are when the total momentum and total kinetic energy is conserved in a collision. Now elastic collisions are collisions where no energy is lost to the internal energy of the surroundings. It is a closed system. Now inelastic collisions are when the total momentum is conserved but the total kinetic energy is not conserved in a collision. So you can see in the following table that if something is perfectly elastic, momentum is conserved, the total energy is conserved, and the total kinetic energy is conserved. But in an inelastic collision, whilst the momentum and the total energy are conserved, the total kinetic energy is not conserved. So to find out whether a collision is elastic or inelastic, you must compare the kinetic energy before and after the collision. Now in reality, there are no true elastic collisions which occur in the universe. However, the collisions between particles can be considered elastic, and the low speed collisions between objects which cause no damage can be considered elastic. An example of this can be snooker balls hitting each other. Another example of this can be a low speed car crash. Now, in a high speed collision of two cars, the kinetic energy could be completely transformed as the cars crumple and deform, leading to an inelastic collision. So, in an elastic collision, all of the kinetic energy is conserved, and the kinetic energy depends on the speed of the object. So this allows us to determine that in a perfectly elastic collision, such as a head-on collision, the relative speed of approach will equal the relative speed of separation. Now, in an inelastic collision, an inelastic collision is one where kinetic energy is not conserved. The kinetic energy is transferred to other stores. So inelastic collisions occur when two objects collide and they crumple and deform. Now, all the kinetic energy of the system may be transferred away from the system and the object can come to a halt. Or it may be that some of the kinetic energy of the system may be transferred away and the objects will move as one body at a speed slower than the original objects. So in theory, a perfectly inelastic collision is when two objects will stick together after the collision. So let's have a look at an example of a question. An object of mass 8,000 kilograms is moving at 3 meters per second and collides with a stationary object of mass 5,000 kilograms. The objects separate after the collision. The 8,000 kilogram object moves at a speed of 1 meter per second. The 5,000 kilogram object also moves. Calculate the loss of kinetic energy in the collision. So it's obviously an inelastic collision because the kinetic energy is being lost. So, the first thing you need to do is work out the term that is missing, which is the velocity of the 5,000 kilogram mass after the collision. So we can use the conservation of momentum. We can say that momentum before equals momentum afterwards. So it's 8,000 times by 3 plus 5,000 times by 0 equals 8,000 times by 1 plus 5,000 times by v. We can work that through, and therefore we can work out that v is equal to 3.2 meters per second. We can then use the kinetic energy equation of a half mv squared to work out the kinetic energy before, which is a half times by 8,000 times by 3 squared, plus a half times by 5,000 times by 0 squared, which is 36,000 joules, and then work out the kinetic energy afterwards, a half times by 8,000 times by 1 squared, plus a half times by 5,000 times by 3.2 squared, which is 29,600. We can then compare the two values and say our energy loss is equal to 36,000 minus 29,600, so it's 6,400 joules. So that brings an end to our lesson today on perfectly elastic and inelastic collisions. So if we've been successful and we've learnt in today's lesson, we can define and describe the conservation of momentum, define elastic and inelastic collisions, and then calculate values in elastic and inelastic collisions. So thank you for watching this lesson on elastic and inelastic collisions, which is part of the Newton's laws and momentum subtopic in the module of forces and motion. Thank you very much and have a lovely day.